Hello, everybody. My name is Shiba Fahad, a student at Macquarie University, offering a Bachelor of Science in Software Engineering. So today we will talk about a cascading symbolic architecture for spatial-temporal academic scheduling, especially in highly non-stationary urban environments. So we talk about what this dynamics spatial-temporal synchronization engine is, what inspired it, what it really does, and much more. We should talk about some related ones and objectives, methodology and architecture, the data description, data engineering parts, the models used and the architectures, and perhaps the training results. We shall also talk about the compression techniques that we use, the payment pipeline, and I will later give references. So for this research-driven development, majorly, we should talk about the problem that really brought us to this, and that was the traditional academic scheduling, especially in high density urban centers, due to these unpredictable local stresses like tropical weather, traffic bottlenecks, and uncommitted administrative events. Give an example. When a lecturer or student gets stuck in the traffic, okay, yes, and they're coming for the lecture. Give an example when the sudden downpour was flooding access routes. You get the point. So this prevents cars from moving or taking students to their destination. Give an example when a lecturer also has unannounced meetings disrupting the schedules that he or she is supposed to be having the lecture in. So all this sum up to a sunk cost effect where students or lecturers are engulfed into this, where their wasted time, wasted fuel, their wasted small transport, especially with the students, is never regained. Okay. So this is what DSTSE was really built for, to solve this frustration. So we shall have then talk about some related works. And what is this all about? Whose work published in 2015. This work really proves that rain shifts the activity durations, okay? Yes, so, but their algorithm that they really used was really static and rule-based. It really lacked that machine learning component. So with Zoo's work published in 2025, it really proved that there is high weather traffic volatility in short-range urban centers. Okay, and this really made them a win of 9.7 cost savings. You get the point. But however, this work really lacked that there is an audit, like the reasoning part, and also the SVM, policy enforcer of the organization. So we also talk about paper published in 2019 that talks about it tells us how important is history data, more reliable, and how it's more reliable than even traffic lights, the rules themselves. So but however, this focused on fixed hardware and really ignored user coordination like students themselves. So with all that said, we came up with a general problem statement that the traditional schedules really fail totally in this traffic environment, and there needs to be a solution for this. Okay, so we developed research questions where which needs answers, and like how can we outsource data, because we found out that we needed that traffic data, weather data, and also administrative events to bring up this to a solid concrete model that is resilient. Okay, so how can machine learning system distinguish between these statistical correlations? Okay, so we generated from the questions and all the reviews, we were able to generate the objectives of this system. One of them, some of them could be identifying the key urban stressors, developing the dynamic spatial temporal simulation that was really put into place, and also implementing that causal audit, just like you will see it later, and evaluating the framework's effectiveness. You'll see all this later, okay? This is our beautiful DSTSE architecture, where we have weather data sensors, traffic sensors, and timetable. So scrap data from the sensors, we preprocess it, we feed into the GRE. The same applies to traffic data. pre-process it, feed into the, then it goes through the Bayesian network, the SVM outputs the processed input, which takes in also the timetable. It extracts features from the timetable, or the Bayesian confidence is high compared to the output of the SVM. It is audited, okay? It audits these outputs. It audits the output of this SVM, okay? And there's an override if need be, especially if the Bayesian proves with a high confidence that a certain condition is severe, okay? So this could be heavy rainfall, is severe. It could override the SVM's policy. So that's an audit as well. Given this architecture that we had proposed, so we need now to go for data engineering or pre-processing, where we had those processes of data engineering as well. So we had the data sets of weather and traffic. So these are the process that we went through in traffic data engineering, okay, before we made more pre-processing. So we got the raw data from the doc, made the round to 15 interval, created a 15-minute grid for each doc, then grouped these docs by actual roads. We created temporal features, interpolated for any missing values, created a complete 15-minute grid, made the calibrations very well. So, and finally, come up with a condition categorization percentiles. So with the weather data preprocessing, here what we did is getting total rainfall, the date, the dry, humidity, wind speed. Then we interpret the missing values. Then also identify the outliers using the interquartile range method. You get the point? So we made more feature engineering by putting in more features, time lags, rows, and also, yes, this way to make our data feature rich for the model to learn on. So when we try to visualize the weather data after the pre-processing, at 21, we had more specs of wet bulb of 21. There were many, they occurred many times, over 160. So the same applies to this. So you can see 21 and around, I think, 23 recorded whatever they appeared many times, okay? Just like you can see here. The same applies here, okay? They occurred many times. 20 dry bulb were recorded many times, okay? 26, around 27, 26. The same applies to this humidity, the same, okay? They have a certain tune that they do follow. So when you see this wind speed, the same, okay? Also the box plot of the categories rainfall, you can see the maximum 30, okay? I can't see it very well. So the same applies to, we can see the outliers in here, okay? Especially with the wet bulb. So we can see that with the wet bulb, we had some outliers here. These were all removed by that interquartile range method, okay? These outliers. So we can see the same here with the humidity by category and for category. We get the point, no outliers, didn't have outliers. So we saw the distribution of these atmospheric variables with rainfall categories just seen here. So we can also see the procession of the time series for these for the total rainfall, okay? Total rainfall, dry bulb, humidity, wind speed, the time series for them, okay? And we see that they have that uniform trend. So when you talk about the histogram for rainfall, we had to further grind more this rainfall because it really mattered a lot, okay? Yes, so with this rainfall, we can see that when we try to see its distribution, some outlier here, it had some over around 80 to 85. Okay, where we had an outlier. I think this was heavy, but those that were didn't qualify to be correct outliers, we interpolated them as well. So the log plus one transformation of rainfall to visualize this more, this was too thin, so we had to make a log transformation. Then we make these small bars more visible, just like you could see. Okay, yes. So this was the data for rainfall, and the data for traffic for this is a correlation matrix after all the feature engineering and pre-processing stuff. Okay, and we could see that the total rainfall, total rainfall, the total rainfall was highly affected by these rollings. Okay, the flags, all the flags really affected them. Okay, but when we come to the category, rainfall category, it was really affected by all those feature engineering, but not as much as the total rainfall. So meaning that regressors could perform better than categorical approach. Okay, yes, just like you could see, this affected it much, but this less. The same here, the same here. You could see this is more dark, this is less. So this traffic data, we visualized it as well. The distribution of rainfall of traffic with a traffic category. You could see that with the very high, we had some outliers where we had more vehicles in over 100. Yes, so, and we could also see the histogram for this of vehicle count, and it was let me see frequency. So this it's around 18. It occurred more often, yes, more often. And also we can see that 40 also occurred more often, 20 something also occurred more often. So we can try to see its progression graph. We can see that in the morning hours of traffic, morning hours, traffic starts to spike at around 4 or at around 5 when people are getting to work, just like you could see here. It spikes up to around 7. Yes, 7. Then it stabilizes. It becomes a constant there, around constant. Then it falls when people, I think, have already reached their working places. It's around 8 or 9. It falls a little bit, but not so down. Then it becomes constant in those days, in those hours. Then it again spikes at around 3:15. 15, eh? 15. It means here people start getting out of their offices, going back home. So that's why it spikes up again. So it again becomes constant, then falls in the later hours till this. So at 10, it stabilizes still. All right, so with the models that we use, we had GRU, the random forest, Bayesian network, and SVM. So after us pre-processing the data that we talked about before, traffic and weather, we had to subject it to various models, especially with the GRU and the random forest. So we'll start with the gated. So what it does, takes in the input as well as the previous hidden state. It processes those inputs through the update gate and reset gate. So here when we put in the new weather readings or traffic readings in the GRU and the hidden state or the previous state, you get the point. So we pass them through the update gate and reset gate. In case we need to add in to update something or reset something, the hidden state or the previous state, all the computations are made here, okay? Then we output a new hidden state, then the output. So with the random forest classifier, what we did was that we also subjected it to all both two types of data, the weather and traffic data, just like the GRU, weather and traffic data. So how does this work is that you have the original training data, you make some bootstrap sampling, then also get random features from random feature selection. Then you make some bootstrap sampling with placement. Okay. Yes, you randomly carry out samples from this bootstrap data. Bootstrap data. Each bootstrap sample is given to a tree. Okay, but with replacement. So when you give in the new samples, especially when you're testing, for the accuracy of when you're testing, or yes, in fact, it's testing, then if she predicts, then you aggregate the prediction. Majority vote, especially for classification, and average, especially for regression. So that's how its architecture is, simply, okay? So with the Bayesian network here, what it does, it's made up of nodes, and specifically ours, it takes in the prediction from any of these models, the best of these models that we shall go with. It takes in the weather prediction and traffic prediction, okay? Then it crashes the delay of the lecture, then it gives a decision. So the SVM for us, it's a graph, so I couldn't put it here. If that was given, okay? So these are the results for the model for the model selection and evaluation. So how here we had the weather and traffic using the GRE and random forest regressors. So the regressors got a 0.7% accuracy, and this got a 0.8% accuracy. The GRE, so we had to take the GRE for this case, okay? My corresponding score was a little bit high compared to this, the regressors. Also for the traffic, we see that the GRE is also performing very high compared to the random forest classifiers. So that is it. So when we get these GRUs, both of them, weather and traffic, so their output is input into the Bayesian network, and here the results, okay? And the Bayesian network was doing pretty cool. When with bad weather and heavy traffic, expect the Bayesian with the expert priors. That's why you can see that with bad weather and heavy traffic, high percentage of online, okay? Also with good and low traffic, high percentage for schedule. You get the point. It was really working pretty fine with these priors, and we are updating it dynamically as well, okay? Yes, on real data, we are feeding it on real data, it's learning continuously. So with the SVM, so the output of here is fed into the SVM to impose the policy. But what's so exceptional is the cancelled and shaded being 0. We can the SVM is saying that online and scheduled are the most safe zone, meaning these are hard targets to hit. Okay, so it's saying that scheduled and online they're the most zones. With the accuracy for this, it was in 6.3, yes, which was pretty cool, but not all that high. So the entire system we had to compress it, but how? We resisted compressing the Bayesian network and the SVM because these were small models, and any small tamper with the structure or the nodes in there, they could result into poor readings. So we had to get the GRUs only, then subject them to compression. And here we have the compression pipeline, okay? We had the original GRU traffic weather GRU, then we created a student, made a layer pruning, weight pruning of the student, then we made the distillation of the students and made the quantization. Then we had the final model. With layer pruning, you're removing many layers or even the nodes themselves, okay? And also reduce the sparsity by pruning the weights, just like you can see here. So we remain with only this layer and this layer, okay? And this other layer will also prune the node. This, why we started with this is because this caused a significant change of structure. You get the point. So we apply the rest of the models onto this already locked in structure. So that's why we went to the node station second, whereby we had to teach now this small student with a teacher's knowledge, okay? Yes, so after that, we submitted the result to quantization, whereby we had to change now the matrices over tensor from the floating point of 32 bits to the 8-bit integers, okay? You get the point. This makes the matrix even very much smaller. However, we can see that there's this other margin metadata of a mapper that also can create some overhead or more memory, can pass some more memory. So that is it. So we get this it8 model, and this is the model that this is a quantity model that we deploy, okay? It's machine friendly, especially for edge computing devices. And remember, this is to be put onto the traffic and sensors, weather sensors. So we have to go through these 4 steps, okay? Layer pruning, weight pruning, node distillation, then quantization to make that fine model smaller but highly accurate and can fit on edge devices. So the traffic compression results are just as listed below. We have traffic model compression and weather model compression. We can see that the context model for the traffic has merged into 8.7 kilobytes with a percentage of 96.29%, which is slightly closer to 96.56 of the original model, okay? With the model the same, it was 146.44 kb to 101.97 kb. Slightly bigger, but the accuracy, it was in 80.63. This was 88. So we can see that these models are small, but highly accurate, okay? So we can see now the deployment pipeline. After us compressing, we had to dockerize the traffic microservices, dockerize weather microservices, and also get the Dockerized decision engine microservices. Dockerize it, the decision engine, that's the SVM and the Bayesian. These were small, we didn't compress them, okay? So we have to also Dockerize the lecture user interface microservice. Then we deploy the model, and you can see that our deployed model. We could see an instance that leads to the Bayesian override, okay? And with the causal reason just right over here, just like you can see, okay? All right, that comes to the end of our good session that covers everything of the DSTSE that has been put to life. We really appreciate Mr. Galwango Marvin for his guidance and feedback. Addison.com, you really did a great job. And Macquarie University for really offering us so institutional support, okay? So these are the references that you can check it out, and the references for the model composition just right here. Thank you. Have a good one.